How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today has more than ordinary enchantment, and I will go at once to it. Consider the following. I have a tin can with some water in it, under which I have put a burner, so that the water has now been boiling for a time, as evidenced by the water vapor seen here condensed, and we call it steam, so that what remains in the vessel now is some water, less than before, and some water vapor. Now I'm going to take the burner away and stopper up the can, and we will witness an astonishing and absolutely astonishing thing. If we listen very carefully, we will hear a certain flexing of the can. What is happening? Some of the water vapor is condensing, the pressure is getting less in the can, and the atmosphere is taking hold. And atmospheric pressure is an astonishing thing. I will hasten the process by pouring some cold water on it. And this is an experiment you can do with absolute enchantment yourself. Here it is. I am going to take the burner away. I am going to stopper this up. I'm going to put it down here. Listen. Oh, but watch it. I'll hasten the process. Oh, there it is. Let me turn it around. There it is. And I say that is something to bear witness to. That is fantastic. The push of the air, staggering in its consequences for the human race. Now listen. The water is boiling inside that can at reduced pressure, at a much lower temperature than 100 degrees centigrade, because the pressure inside is less than 1 atmosphere. This is fantastic. Fantastic. Let me show it to you another way. Here I have another tin can, and I'm going to connect this tin can to a vacuum pump, which permits me to pump out some of the air, and just a little of it. I could never pump it all out. If I pumped for 1,000,000 years, I couldn't get it all out. Why? Too many molecules in there. But let me... There it is. There it is. There it is. The push of the air. Staggering to witness. Staggering. Show it to you another way. Take a look at another piece of apparatus. I have a funnel. A funnel. And across the top of it is a sheet of rubber tubing, as from an automobile inner tubing. The air inside is at atmospheric pressure. I'm going to connect the vacuum pump here and reduce the pressure inside from atmospheric less and less and less and less. And the rubber sheet, suffering the forces, the push of the air, will be depressed inside deeper and deeper and deeper. And indeed, if it can endure the reduction in pressure and the push of the atmosphere, I shall be surprised. Very likely, it will be torn apart. Here it is. There's the rubber tube. I am going to connect this. Now, I'm going to reduce the pressure. There it is, getting pushed in. There it is, getting pushed in. Oh, man, this is something. I'm going to stop it a minute. Let's get a tight shot, if you will, of that. And notice the enormous push of the atmosphere. Fantastic. Now, I'm going to evacuate more and more and let the push of the air push that more and more. And I'm going to step aside, because when this does indeed burst, it has a detonation which could, well, unseat this building. That'd be very good. Oh, I like to do this once in a while because it adds to the drama of the matter. It adds to the drama. Oh, there it went. There it went. I hadn't expected it, really. But notice the enormous forces of the air. How enormous? Well, only about 15 pounds per square inch at sea level. Let me remind you of the consequences. The ordinary human being has about 3,000 square inches of surface. 3,000 square inches of surface. 3,000 square inches. If you skinned an ordinary human being, laid out the skin and measured the projected area, it'd be about that. On every square inch, there's about 15 pounds. 45,000 pounds is the push of the air on me. Over 20 tons. Is there any wonder why at the end of the day a fellow goes around all worn out, carrying that load of air? Now, to show you further the consequences, consider these things, which we need to look at sharply, acutely, circumspectly, because what is said about them is always wrong. They are called suction cups. Suction cups. And I must advise you to put the word suction out of your vocabulary. It is unacceptable. Why? Because there is no suction, no such force. What do? Let me squeeze them together, face upon face, and what have I done? I have squeezed the air out from between them. Now, why are they held together? They are held together because of the push of the air. I could compute it very readily. If, let us say, I have squeezed out all the air inside from between them, all I need to do is measure their area. Pi r square is the area of a circle. And that area in square inches times 15 pounds per square inch. Indeed, it turns out that about 300 pounds is necessary to pull these apart. There, about 300 pounds necessary to pull them apart. Of course, look at the usefulness. Look at that. Indeed, regarding the usefulness, the next time you watch people who change big panes of glass in department store windows, you will notice the pane of glass weighs half a ton and 3-4 men carry it. How? By fixing a so-called, forgive me for the use of the language, so-called suction cups, and then they carry it around. The push of the atmosphere. Now, I used a vacuum pump in this, and you should read about Otto von Guericke, Guericke, who in the 16th century invented the vacuum pump. And I want to show you his first one, if we can get a tight shot of that. There we are. Notice, here is a pump with a piston and 2 men are drawing on it, and he reports in his report to the societies, the scientific societies, that there was first a slight hissing as by bees and birds, and then bang, the cask collapsed. Here is another one showing the same. Fantastic. Those 2 hemispheres put together, the original Magdeburg hemispheres. And here is a picture of von Guericke. So we should pay him tribute. We should pay him tribute. Now, I have spoken of the Magdeburg hemispheres. Let's take a look at them. Here they are in replica. 2 hemispheres made of steel, which I put closely face to face. And then I connect the vacuum pump, and the valve is open, and I take out some of the air. I take out some. Never all, could never take it all out. Then I'm going to close the valve, shut off the pump. Now I'm going to try to pull them apart. Never, not 1 man alone, indeed 2 could hardly do it. So I'm going to do something. Obviously, the pressure inside is too low. The push of the atmosphere outside is too big. I'm going to do something. Watch. Listen. Listen. I'm going to open the valve instantaneously. There. Now, what did I do? Oh, some say you let some of the vacuum out. Oh, that murders me. As Macbeth doth murder sleep. Didn't let any of the vacuum out. I let some air in. Still too much. Let more of the vacuum out. Oh, now I let so much out that all of it's out. And so we have the Magdeburg hemispheres, a classical demonstration, historically, of atmospheric pressure. One more very dramatic one. On an earlier program, I showed this when I talked about inertia. But I want to do this now because it is a demonstration of atmospheric pressure. You see, ladies and gentlemen, boys and girls, what I'm trying to do is not teach any physics in these recitations, but rather stir your interest by events which are dramatic for the soul. Here is a sheet of paper, about 20 inches one way and 30 the other, 600 square inches. On each square inch, 15 pounds, 600 times 15, 9,000 pounds of air. And you know, as I did before, I'll do it once again. I cannot move the weight of that air. There it is. And I say that is staggering to contemplate, the push of the air. Of what usefulness is this? Oh, well, without air, birds couldn't fly and airplanes couldn't fly. Indeed, talking about flying, here is an instrument called an altimeter, or altimeter. What does it consist of? It consists of a little chamber which is highly evacuated. I'll draw that little chamber which is highly evacuated. Here it is, highly evacuated, and it has a lever system on it with a scale. Now, we go high into the atmosphere, air ends a little, the cover lifts up and leaves on. So we get a reading of the attitude in terms of the air. Or, if you wish, another use made of the atmosphere, which has so much to do with the events of weather. Here is an aneroid barometer, which has inside it exactly the same thing. The response of the chamber to increase and diminution of pressure gives rise to a reading, and I invite you to look up the word aneroid, because what does it mean? It means without, a meaning not, and neros, wet, without wetness, so it is not a mercury in glass barometer, but a dry barometer. And talking about a mercury in glass barometer, here's something you can do. Take a long glass tube about 1 meter long and fill it with mercury. It's closed at one end, fill it with mercury. Then take a vessel in which some mercury resides, turn the tube upside down, a finger across the open end, submerge the open end in this vessel of mercury, and take your finger away. Remember, the tube is filled with mercury. What would you expect? You would expect all the mercury to fall out. No, it does not. It's to a certain level, and notice the shape of the meniscus, the shape of the surface. It falls how far? So that this length is about 76 centimeters, or about 30 inches. And that is 1 atmosphere which sustains this column of mercury. And here is a region highly, highly empty of everything, except a little mercury vapor, perhaps. So one of the best vacuums we can get is produced by such a performance of a mercury column in a glass tube. Now let's see what else we could show. What else could we? Look at this. Isn't this fantastic? Indeed. Oh, I have another one. And since it enchants me, I'm going to do it. This was boiling over there. Here it is. Notice. I'm in a hurry. Listen. There it goes. Notice, I thought I had not boiled the water long enough, because if there was any occluded air in there, we would have trouble. And so, are you not agreed that atmospheric pressure is a staggering thing to witness? And I thank you for listening.